Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 13 on more work with the tangent function. It's pretty important that you saw Lesson 12 before taking a look at this because I'm going to assume that you have some familiarity with the tangent function and how to calculate the tangent values for the special angles as we jump into it. So, without further ado, let's talk about more issues with the tangent function. We're going to begin by discussing the symmetry of the tangent function. Although sine and cosine are by far the most important, the tangent function, which is the ratio of sine to the cosine, is also a very important function. So let's take a look at exercise number 1. For each of the following pairs of angles, determine the values of each of the angles' tangent in simplest radical form. So for letter A, I want to figure out what the tangent of pi over 4 is, and what the tangent of negative pi over 4 is. Now remember, negative pi over 4 is just going to be a clockwise rotation by pi over 4 radians, so it's going to be the coterminal with 7 pi over 4 down here. So let's just recall how we do this. Now, I get to do the really easy one, right? Because tangent of pi over 4 is equal to the sine of pi over 4 divided by the cosine of pi over 4, which is root 2 over 2 divided by root 2 over 2, which is equal to 1. The tangent of pi over 4 is equal to 1. Now remember what we talked about in the last lesson. We can also think about tangent as being the slope of that terminal ray. And again, I hope that you can appreciate that that slanted line has got a slope equal to 1. Now, if I was going to negative pi over 4, which is right here, right, we can also calculate its tangent value, and we can say that the tangent of negative pi over 4 is equal to the sine of negative pi over 4, pi over 4, divided by the cosine of negative pi over 4. And that's then going to be negative root 2 over 2 divided by positive root 2 over 2. And that's going to be negative 1. And again, I think you can probably get a good sense for that slope being negative 1. Okay, great. So the tangent of pi over 4 is 1, and the tangent of negative pi over 4 is negative 1. And now we're going to get into some of the more messy ones. So let's take a look at pi over 3 and negative pi over 3. What I'd like you to do is pause the video right now and see if you can come up with the tangent of pi over 3 and likewise the tangent of negative pi over 3. We did at least tangent of pi over 3 in our last lesson, so hopefully that looks familiar. Now again, if you're thinking about the tangent of negative pi over 3, you just need to sort of go down to here to 5 pi over 3, right? And so we're talking about those two angles like that. Why don't you pause the video now and try to come up with those two tangent values. All right, let's first take a look at pi over 3. All right, I'm trying to kind of keep it there as well. So the tangent of pi over 3, which is going to be the sine of pi over 3 divided by the cosine of pi over 3. That's going to be the square root of 3 over 2 divided by negative positive 1/2. I don't know why I'm having such a problem here. We're talking about this coordinate pair. A little stay change or keep stay change. Square root of 3 over 2. This is my reminder not to try to talk and write at the same time. Those cancel and we find that the tangent of pi over 3 is root 3. Okay. Now if we want the tangent of negative pi over 3, we're going to be dealing with that coordinate pair, 1/2 comma negative square root of 3 over 2. So the tangent of negative pi over 3 is going to be negative square root of 3 over 2 divided by 1/2. That's going to be negative square root of 3 over 2 times 2 over 1. Those cancel and we get negative square root of 3. Great. All right, let's do one more. Here we go, pi over 6 and negative pi over 6. Again, keep in mind, right, pi over 6 right here. negative pi over 6 right there. Why don't you go ahead and try to find their tangent values? These are going to be probably the ugliest of them all. Go ahead and pause the video and do those two. Okay, here we go. So the tangent of pi over 6 will be the sine of pi over 6 divided by the cosine of pi over 6, which will be 1/2 divided by square root of 3 over 2. All right, which will be 1/2 times 2 over the square root of 3. Those 2's cancel, and we have 1 over root 3. We'll do a little rationalizing of the denominator by multiplying top and bottom by root 3. And we'll find that the tangent of pi over 6 is the square root of 3 over 3. Tangent of negative pi over 6, you're not going to probably be surprised by this one, will be the sine of negative pi over 6 divided by the cosine of negative pi over 6, which will be negative 1/2 divided by positive root 3 over 2. That will be negative 1/2 times positive 2 over root 3. Yet again, the 2's cancel. I get negative 1 over root 3. When I rationalize, yet again, I will get negative square root of 3 over 3. All right, so this all leads us, besides just reviewing how to calculate the tangent for some of the special angles, this leads us all to letter D. Based on your results from A through C, does the tangent function appear to be an even function, an odd function, or neither? Explain. All right, pause the video right now and see if you can remember the definitions of what makes something an even function, an odd function, or then if it's neither one of those, then neither. Well, this happens to be an odd function. At least it appears to be, because opposite inputs resulted in opposite outputs, right? So if we look, and there's our red, right? If we look at pi over 4 and negative pi over 4, right? Tangent of pi over 4 was 1. Tangent of negative pi over 4 was negative 1. Opposite inputs resulted in opposite outputs. And we saw the same thing occur for pi over 3, right? The tangent of pi over 3 was square root of 3. The tangent of negative pi over 3 was negative square root of 3. And you can really see that, right, with the slopes, right? The slope of that and the slope of that really are the same, except that's a positive slope and that's a negative slope. And in fact, let's now formally prove this in the next part of this worksheet. Proving tangent is an odd function. We can use the unit circle to better understand why the tangent function must be an odd function. That is, it results in opposite outputs for opposite inputs. So let's try to understand that using the unit circle, not using special values. Exercise number 2. The unit circle is shown below with a positive and negative angle with the same absolute value drawn. The positive angle intersects the unit circle at the point A, B. Letter A. At what point will the negative angle intersect the circle in terms of A and B? Right? So in other words, and you can actually even look back at our work in exercise 1 to be able to think about this, right? If I go theta in this direction and theta in that direction, right? It just happens to be like negative theta there. And let's say we intersect at positive A, B. What will be the points down there? Pause the video now and go ahead and let me know that. Well, the A coordinate wouldn't change, right? This is just a reflection across the x-axis, but the B will be negated. So we'll be at the point A, negative B. And why don't we draw that on the diagram, right? We'll be at the point A, negative B. Wonderful. Letter B. Write expressions for each of the following in terms of A and B. All right, This should be easy. Why don't you go ahead and do that based on right triangle trigonometry, or based on the definition that tangent is sine divided by cosine. All right, well, tangent is sine divided by cosine, so tangent of theta will be b divided by a, and tangent of negative theta will be negative b divided by a, which is just negative b over a. And now you probably see it. Let's take a look at letter C. How does letter B prove what you noted in exercise number 1D? In other words, in exercise number 1D, we noted that for tangent, opposite inputs gave us opposite outputs. Well, it's literally right here. In other words, right, the tangent of negative theta will be negative b over a, which is negative tangent of theta, right? And that is the definition of an odd function. You know, f of negative x is negative f of x. Tangent of negative theta, make sure that that negative is really kind of there. Tangent of negative theta is negative tan theta, because this just is tan theta. And again, I really like it from that slope perspective too, right? When I look at these two rays, right, this one has a run and this one has a run that's the same. They have the same run, but their rises are opposite of each other, right? So you can really see why that tangent is an odd function, all right? Now remember, sine was also an odd function and cosine was an even function, okay? But tangent ends up being kind of, you know, an odd divided by an even, and strangely enough, that ends up being an odd function. Okay, so let's talk again about locations where the tangent function is undefined. And we looked at this in the last lesson, so this should be kind of covered ground. But unlike sine and cosine functions, right, the tangent function is not defined for all real values of the input. We looked at this some in the previous lesson, so let's just take a look at it again in exercise number 3. Given that y equals tangent of x equals sine x divided by cosine x, give values of x on the interval negative 2 pi is less than or equal to x is less than or equal to 2 pi, where this function would be undefined. Explain why it would be. All right, now I know our unit circle is really only going 0 to 2 pi, but I also want to be able to think about it as 0 to negative 2 pi as I go clockwise around it. So see if you can remember from our last lesson why this would be undefined, and as a reminder, division by 0 is always undefined. Pause the video now and see if you can figure out the angles at which tangent would be undefined. Okay, well, tangent of x will be undefined anytime cosine of x, whoops, I shouldn't do that, if cosine of x is equal to 0, right? We can never have a 0 in the denominator. So tangent of x will be undefined if cosine of x is equal to 0. Well, where is cosine x equal to 0? On the unit circle, right? Cosine is the x-coordinate. Don't get that confused with this x. They have nothing to do with each other. This x is an angle. On the unit circle, x is just the x-coordinate. So where will cosine x be equal to 0? Well, that's going to be here when x is equal to pi over 2. It's going to be down here when x is equal to 3 pi over 2. That's if we're going counterclockwise. And if we go clockwise, wow, that was meant to be in red, and it just didn't get there. And if we go clockwise, that will be at negative pi over 2 and at negative 3 pi over 2. Don't forget that last time we talked about the fact, and we reminded you of this earlier in this lesson, that the tangent of an angle can also be thought of as the slope of the terminal ray of the angle. So if we've got a terminal ray that points straight up or straight down, we're talking about a vertical line where the slope is undefined. All right? But what we know for certain, if we took our calculator out and we asked it what the tangent of pi over 2, 3 pi over 2, negative pi over 2, or negative 3 pi over 2 was, it would tell us undefined. And that is going to actually have an effect, a big time effect, on what the graph of y equals tangent x looks like. So let's take a look at that in the next exercise. The graph of the tangent function. Because of the locations where the tangent function is undefined, its graph is far more complex than that of sine or cosine. It will have vertical asymptotes at each location where the cosine function is equal to 0. All right? And that's really kind of cool. We saw vertical asymptotes at really only one other point in this course, and that was with logarithmic functions, the inverses of exponential functions, right? Exponential functions had horizontal asymptotes, logarithmic functions had vertical ones. But now we'll see another function that has vertical asymptotes, and that's the tangent function. Logarithmic functions just have a single vertical asymptote, oftentimes the y-axis. Tangent has an infinite number of them. So let's take a look at exercise number 4. Given the function f of x equals tan x on the interval negative 2 pi is less than or equal to x is less than or equal to 2 pi, do the following. Letter A. Draw vertical dashed lines at each location where f of x is undefined. List these values below. All right, so remember what we just saw was that tangent was going to be undefined at negative 3 pi over 2, at negative pi over 2, at pi over 2, and at 3 pi over 2. Now, vertical asymptotes are not actually part of a graph, right? They are a vertical line that the function approaches but never touches. So we draw those in dashed. We're going to draw in a dashed vertical line at x equals 3 pi over 2, a dashed vertical line at x equals pi over 2, x equals positive pi over 2, and x equals 3 pi over 2. Now, whatever happens to tangent, okay, no matter what the graph looks like, as it gets very close to these dashed vertical lines, it's going to go haywire because it can't touch them. It can't have a value there, all right? And we expect it to look more and more like those vertical lines as we get closer to it. But we're going to bring in our calculator now. Let's take a look at letter B. Use your calculator to graph the tangent function using the window shown. All right, great. So let's go ahead and do that. Let's open up our calculator. Let's add a graph. Make sure your graph is in radian mode, and it's going to be the simplest of all tangent graphs. Love it. Here we go. All right, now even just hitting enter now. All right, we end up having a crazy wacky graph, okay? But I want to get my window to look like the one here. So I'm going to go into my window settings. We're going to go from negative 2 pi to 2 pi. I want to make that graph scale by, I think we'll make it scale by pi over 2 units. That's okay. The scale is actually pi over 4 on there, but I think we'll keep it at pi divided by 2. The y doesn't matter too much, but just to keep with the scale that we have on there, negative 10 to 10. And we'll go with that by ones. And we'll hit OK. And there it is. There's my tangent graph, at least over here. Now, my graph is not showing me those vertical asymptotes, all right? That's those vertical lines that occur here, 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 and here, right? So now I can sketch it in. Let's just concentrate on that portion from negative pi over 2 to pi over 2. Notice it does go through the origin. The tangent of 0 is 0. All right. Again, just kind of showing that. I put arrows down here and up here because the graph does extend up to infinity and down to negative infinity as it approaches negative pi over 2 and pi over 2. And then it just keeps repeating itself. So I get exactly the same waveform right over here. And it would keep doing this, all right, no matter what. I just run out of space, if you will. So something like that and like that. And again, As we've talked about with sine and cosine, tangent's graph continues forever towards x equals infinity and forever this direction in terms of x equals negative infinity, but I've only got this portion between negative 2 pi and 2 pi. All right, let me put that away for right now. Come on, there we go, view full screen. All right, let's take a look at letter C. How does the symmetry of the graph verify the fact that f of x equals tan x is an odd function? All right, so now that we've got its graph up, we can think about that odd-even business in terms of symmetry. What kind of symmetry did odd functions have? Pause the video now and see if you can recall that. Well, it's symmetric about the origin, and it's probably easiest to see by just looking at this sort of form that goes from negative pi over 2 to pi over 2. In other words, if I rotate that thing about the origin by 180 degrees, that portion would land on that, and that portion would land on that. All right, I wonder if I could even do that. Yeah. Well, okay, so I didn't draw it the best. But in theory, it should land on top of itself. I gotta stop doing things like that. All right, here we go. So it has symmetry across the origin. All right, awesome, symmetry across the origin. Now finally, let's talk about letter D. There's a much nicer graph. The period of the sine and cosine parent function is 2 pi radians. Is this also true for the tangent function? So in other words, we know that for sine and cosine, they are going to repeat their fundamental pattern at the very smallest interval being 2 pi radians. Is the period of tangent 2 pi radians? Obviously it repeats itself, right? This repeats this, repeats this. But the question is, if I took this and I shifted it over, would I have to shift it over 2 pi radians in order to make it land on itself? Or is there a smaller or larger amount that I would need to shift it over? Pause the video now and think about that for a moment. See, the period for tangent is not 2 pi, it's only pi radians now. And you can really see that, I think, best by taking this point here and shifting it over to here to this point. That is only pi radians. The period of tangent, and I'll say y equals tangent x, is only pi radians. It certainly repeats itself every 2 pi radians, but that would be 2 periods as opposed to 1 period. All right, let's take a look at one last problem. The tangent function is not normally used to model wave or cyclic phenomena the way that sine and cosine functions are. All right, so we're not going to be talking about the tides rising and falling according to the tangent function. We're not going to be talking about light waves being described by the tangent function. But it can still be involved in various problems. The tangent functions involved in these problems may have had various transformations done to them. All right, so you can still take a tangent function and you can stretch it vertically, you can shift it vertically or horizontally, you can, compress it or expand it in terms of the horizontal dilations. You can do all of that. Now, you don't necessarily particularly have to get into that. You are expected to know about the basic tangent graph, absolutely, at this level, but you don't necessarily have to know about all the different transformations of the tangent graph. We'll get into those more in pre-calculus. Let's take a look at exercise 5, though. Solve the inequality below. Round all values of x to the nearest hundredth. Justify your answer. Well, it wouldn't matter whether or not we were in this course, pre-calculus, AP calculus, or any other course. The only way to solve this inequality is to solve it graphically. So what I'd like you to do is pause the video right now and see if you can produce a graph that will allow you to think about this inequality and solve it, get an interval of values of x that make this true, where the endpoints of that interval are rounded to the nearest hundredth. Why don't you go ahead and do that? And again, it's kind of cool because even without having to understand exactly what it looks like, this particular side of the inequality, 3 times the tangent of 0.5x, it's been stretched vertically by a factor of 3, and it's been actually stretched horizontally by a factor of 2, right? That whole, reciprocal of 1/2 business. I don't need to know that. All I need to do is produce an appropriate graph. So let's take a look. I'm going to bring this thing over here so that we can see that inequality. I'm going to open up a brand new document, and let's do it. Let's add a graph, and in f1 of x, I'm going to put in 3 times the tangent of 0.5x. Awesome. And then in the second one, maybe I'll get the second one in there. I'm going to have 6 minus 5x squared. Okay. And there, right, we've got our 2 functions. Now, right, it's not entirely clear to me what the interval is, but I can really kind of get a good sense for it right here. Now remember, I'm looking for where the tangent graph is less than or equal to this quadratic graph, right? And that's going to be between those particular 2 intersection points, right? The tangent graph will be below those 2 particular intersection points. So what I need to do is I need to find the intersection points. That's simple enough by going into my menu, analyzing my graph, finding my intersections. So, whoops, come on, keep going over this way. I hit enter, I move it this way, hit enter. Oh, that is just not what I wanted to do. And there's just no control Z on this thing. Sorry about that. Let me go back into graph edit, function. I cannot believe it just completely changed F2. That is insane. Bad TI Inspire, bad. 6 minus 5x squared. Okay, there we have it again. There's my intersection point. Thank you very much. All right, now we'll find the other one. Menu. Analyze. Geez, sometimes. Here we go. Enter and enter. There's my other intersection point. So what we can now see, right, is that our tangent graph will be less than or equal to our quadratic graph between this x value and this x value. So now we just want to sketch an appropriate graph. We're looking to round this to the nearest hundredth. So let's get ourselves a good sketch. And again, it doesn't have to be in any way, shape, or form perfect, but we might do something like this. Oh, that was less than perfect, I'll say. Something like that. Label my intersection points. This is at 0.95, comma 1.53. This one is going to be at negative 1.28, comma negative 2.24. Let me just kind of verify. Yep, those look good. Excellent. Right, I'd want to label my curves. I would say that this is y equals 3 times the tangent of 0.5x. This one is y equals 6 minus 5x squared. I also want to label my window, whatever that window is, maybe negative 10 to 10 and negative 10 to 10. I don't think that's quite what my window is. But then I can say that this is going to be true for all values of x greater than or equal to negative 1.28, less than or equal to 0.95. And again, this is just a reminder, really, of how to solve an inequality graphically. Like, we are literally saying, where is this curve at or below this curve? That's all we're asking. All right, let's wrap this up. Again, we would solve this problem the same way, whether there was a tangent sitting here, a log sitting here, a square root sitting here. We would graph this side, and then interpret like which one has to be above the other, etc. All right, so today we worked a little bit more with the tangent function. Specifically, we got some more work on just finding the tangent of those special angles like pi over 4, pi over 3, and pi over 6. And we really kind of dug into the symmetry of the tangent function and why the tangent function must be an odd function, right? Why, If I gave you the tangent of 5 pi over 6, you could say that the tangent of negative 5 pi over 6 was simply the opposite of it, right? So we really kind of dug into why tangent is an odd function based on the symmetry of the unit circle and, of course, how the tangent function is defined. We also briefly took a look at the graph of the tangent function and why it must have vertical asymptotes where the cosine of an angle is equal to 0, right? Where the tangent is undefined. And finally, we took a look at that last little problem where we solved an inequality involving a tangent function graphically. All right, well, we've got one more lesson in Unit 11 where we're going to, introduce you to three more trigonometric ratios, all right? And we're going to see those, work with them a little bit in terms of special angles, and we'll revisit the sine, the cosine, and the tangent at that point as well. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.